Morning friends, in this chapter of today's we discuss about the interference. Now the second phenomena of light, there is the diffraction. What is the diffraction? We are going to discuss, and also we discuss about the pattern, the interference, like the same pattern of the interference is obtained in diffraction. Here also the interference take place, and constructive and destructive interference also take place in diffraction phenomena. Here also we are going to discuss about the fringes, bright and dark fringes, but in diffraction, what are the fringes are obtained are not same in weight and also same in intensity. Here the intensity gradually decreases as the order of the fringes increases. Okay. Now first we are going to discuss what is the diffraction. The phenomena of wave around the obstacle or the opaque is known as the diffraction. That means when the light wave is incident on one obstacle, at the edge of this obstacle there is a bend. So this phenomena is known as the diffraction. Diffraction phenomena is occurred due to the limited portion of a wavefront. Limited portion of a wavefront. First, the definition of the diffraction. The phenomena of wave around obstacle or the opaque, around opaque or obstacle is known as diffraction. We can also define the phenomena of diffraction like that way. Diffraction is the physical effect produced due to limited portion of a wavefront. So anyone is the definition we can define. First, what is the phenomena of wave around the obstacle or the opaque? That is known as the diffraction. And second is the diffraction is the physical effect produced by the limited portion or the limited part of a wave. Diffraction was first discovered by the scientist name is Grimaldi. Diffraction first observed by or discovered by scientist named Grimaldi. Now next is the diffraction phenomena occurs in which type of the wave? Sound wave, light wave, water wave and matter wave. Diffraction phenomena occurs in sound waves, light wave, water waves and matter waves. Next point is that the diffraction depends on wavelength of a wave lambda and also the width of a slit. Diffraction depends on wavelength of a wave wavelength lambda of a wave and width t of a slit. It means it depends on ratio lambda upon d. Lambda upon d. If the lambda upon d ratio is small, so diffraction of the wave is small. If the lambda upon d is less, so here the diffraction is less. If lambda upon d is small, diffraction is more. Diffraction is more. So this way, there is the first discovered by the Grimaldi. Now the phenomena of diffraction is take place in sound wave, light wave, water wave, and also the matter wave. Diffraction is depends on the wavelength lambda of a wave and width t of a slit. That means that it depends on lambda upon d ratio. Okay. If the lambda upon d ratio is small, so diffraction of the wave is also more. Now, next is our eye or the optical devices like a telescope, microscope have a limit on the resolving power due to the diffraction phenomena. Our eye and optical device telescope and microscope have a limit on resolving power due to diffraction. So due to the phenomena of diffraction, our eye and also the telescope and microscope has some limitation on the resolving power. The colors on CD, the colors appearing on CD is due to the diffraction. As the diffraction takes place on the surface of a CD, so we shown the surface of a CD is of multicolor. And the diffraction phenomena can explain only by the wave concept. The diffraction can explain only by wave theory. It means by considering a ray with the particle nature of a light, we can explain the diffraction phenomena. Diffraction are two types. First, if the spherical waves are incident on the slit, then the diffraction is known as the Fresnel diffraction. If spherical wave incident on a slit, the diffraction is Fresnel diffraction. That means what are the waves are incident on a slit are the spherical. So such diffraction is known as the Fresnel diffraction. And next is if plane wave front or the plane waves are incident on a slit, The diffraction is known as the Fraunhofer. The diffraction is Fraunhofer. Fraunhofer diffraction. So there is the basic information about the diffraction. Now again, what is the phenomena of the diffraction? The phenomena around the obstacle or the opaque, that is known as the diffraction. Diffraction is also defined as a physical effect produced by limited portion of a wavefront, that is also known as the diffraction. Now, diffraction first discovered by the scientist named as the Grimaldi, and diffraction phenomena occurs in different types of the wave: sound wave, light waves, water waves, and matter waves. Diffraction depends on the wavelength lambda of a wave and the width of a slit. That means depends on lambda upon d ratio. As the lambda upon d ratio increases, so diffraction of the wave is also more. Now, our eye and other optical devices like as the telescope, microscope have a limit on resolving power due to the phenomena of diffraction. Now, the colors appears on a CD is due to the phenomena of diffraction. Now listen, the diffraction can explain only by the wave theory, not the particle theory. Okay. Now the diffraction are two types. One is if the spherical waves are incident on a slit, the diffraction is known as the fresnel diffraction, and if the plane waves are incident on a slit, the diffraction is known as the Fraunhofer diffraction. In our syllabus, only the Fraunhofer diffraction is in our syllabus. That means the parallel waves are incident on a slit. After the diffraction by a slit, also the waves are plane. Here we have to discuss the Fraunhofer diffraction, and on the basis of the Fraunhofer diffraction, we have to discuss about the central maxima, first order minima, and first order maxima. Okay. Now, on the basis of the diffraction of the phenomena, some phenomena take place in our daily life like today. We can listen the voice of the person outside the room, but we can't see that person. So there is due to the phenomena of diffraction. Okay, now on the basis of the diffraction, in our daily life, the daily occurrence, this type of the phenomena, the person standing behind the open door inside the room can listen the voice of the person standing on the other side of the door, that means outside of the room, but they can't see each other. Explain this phenomenon. Now we know that the wavelength of a sound wave, wavelength of the visible light is 4,000 angstrom to 7,000 angstrom. For simplicity, we consider the average wavelength of the visible light is 6,000 angstrom. That means the 6 into 10 is to minus 7 meter, right? And if the width of a door is 1 meter, therefore the ratio lambda upon d is 6 into 10 is to minus 7. So already we discussed about that the diffraction phenomena depends on the lambda upon d ratio. Lambda upon d ratio. Now, the average wavelength of visible light is 6 into 10 is to minus 7 meter, and the width of the door, width of a window or a door is d is equal to approximate 1 meter. Therefore, lambda upon d ratio is 6 into 10 is to minus 7 meter upon 1 meter. That means the 6 into 10 is to minus 7. That is very, very small. This value is very small. Thus, diffraction of visible light is negligible. That means the very small diffraction takes place for the visible light. Therefore, the wave of the light can't bend at the obstacle or the edge of a window. While frequency of normal sound is 100 Hz to 400 Hz. So the average frequency of sound wave is, we consider 330 Hz. There is the lies between this value of 100 to 400. And speed of a sound wave in a medium, is 330 meter per second. Therefore, wavelength of sound wave lambda is equal to C upon F. Therefore, 330 upon 330, that means approximate 1 meter. And width of a door D is equal to 1 meter. Therefore, lambda upon D ratio is 1 by 1 is equal to. So that is maximum value for diffraction. That is maximum value of diffraction. The maximum value of lambda upon D ratio for maximum. Therefore, for sound wave, the sound wave band 4, or the band at angle 0 degree to 90 degree. Therefore, maximum diffraction occurs in sound wave. Thus, the person inside the room can listen the voice of a person outside the room, but they can't see each other. Now here, the answer of this question depends on the ratio lambda upon D for the sound, for visible of the light waves, and also the sound wave. We need to find out the ratio lambda upon D. For the light waves, here the wavelength of a light wave is 4,000 angstrom to 7,000 angstrom. Here we consider the average wavelength of a light wave is 6 into 10 is to minus 7 meters. And the width of a door or the window is 1 meter. Therefore, lambda upon d is 6 into 10 is to minus 7 meter, which is very, very small. Therefore, the diffraction of the visible light is negligible. Therefore, the wave of the light not bending at the edge of the obstacle. While the frequency of the normal sound wave is between 100 Hz to 400 Hz. Okay. When we are talking at that time, the frequency of our voice is this range, 100 Hz to 400 Hz. So the average frequency of the sound wave is, we consider 330 Hz, that is lies between this minimum and maximum value. Therefore, what is the wavelength corresponding to this frequency? We know that the velocity is equal to f into lambda. That is the frequency into wavelength. Okay. Therefore, wavelength is equal to velocity upon the frequency. 330 upon 330, that is the 1 meter approximate. Therefore, the width of a door is also 1 meter. Therefore, lambda upon d is approximate 1. So there is the maximum value for diffraction, and therefore the sound wave bend at any angle 0 to 90 degree angle. Therefore, our sound wave can easily bend at the edge of a door at any angle. Thus, the person inside the room can listen the voice of a person outside the room, but they can't see each other. Clear this? Okay. Okay, now just we discuss about the two type of the diffraction, Fresnel and Fraunhofer diffraction. Now, Fresnel diffraction. In Fresnel diffraction, the waves incident on a slit are spherical wave. That means here we do the diagram for the Fresnel diffraction. Here from the point source S, here the waves are incident on a slit. That is the slit. So here these waves are spherical, are incident on a slit. So as a result, according to the Huygens principle, all the waves, all the point on this slit behave as an independent secondary source and produce the secondary spherical wave. These spherical waves are generated from each and every points of a slit. So these waves are propagated in the medium and superpose on each other. And according to the path difference at a particular point on the screen. Now there is the screen. At different point, the different phenomena, that means that this point are shown the bright dark. That means the fringes are obtained. Bright dark. This type of the waves, fringes are obtained. So this phenomena is known as the Fresnel diffraction. In Fresnel diffraction, the incident wave and also the waves superposed on each other are the spherical wave. That means the distance between the slit and source is very, very small. Slit, screen, and that is the source. The distance between source and slit and screen is limited distance, that means the short distance. Now, for Fraunhofer, second type of the diffraction is Fraunhofer diffraction. In Fraunhofer diffraction, the incident waves are plane wave. Plane wave, that means here the plane wave front, that means the light coming from the far distance. Light coming from the far distance. In laboratory, how we obtain the parallel waves or the parallel rays. For that purpose, we are using the convex lens. If the source of the monochromatic light is placed at principal focus of a convex lens, therefore, the rays reflected by the convex lens are the parallel, are the plane wave thread of the parallel wave. This incident on a slit. So as a result, each and every point on the slit, according to the Huygens principle, behave as a secondary source and produce the spherical secondary waves. These waves are superposed on each other. And as a result, these are the spherical waves. Keep in mind that these are the spherical waves. During the propagation, they are superposed on each other. These spherical waves are again with help of a convex lens. They are focused at a particular point on the screen. So this type of the ASI is shown in Fraunhofer diffraction. There is the Fresnel diffraction, there is the Fraunhofer diffraction. So here are two types of the diffraction, Fresnel, Fraunhofer. There is only for our understanding or the knowledge. In Fraunhofer diffraction, the incident and reflected waves are plane waves, while in Fresnel, the incident and reflected waves are spherical waves. Here the distance between the source and slit and screen are the finite distance. Here the distance between the source and slit and also slit and screen are infinite distance. In Fraunhofer diffraction, two convex lenses are used, L1 and L2. While in Fresnel diffraction, no any lenses are used. Okay, here we are going to discuss about the Fraunhofer diffraction by a single slit. How we obtain, or what is the arrangement for the Fraunhofer diffraction by a single slit. So here the arrangement is this. A source of monochromatic light is placed at the principal focus of a convex lens. Therefore, the light emerging out from the lens is plane wave or the behave as a plane wave thread incident on a slit. So, according to the Huygens principle, all the points in the slit behave as the independent secondary source and produce the secondary spherical wave. These spherical waves are propagate in the medium and superpose on each other. These superposing waves are focused on a screen at particular point by the other convex lens placed at principal focus. And as a result, we obtain the dark and bright fringes on the screen. Due to the constructive and destructive interference taking place on the screen. Okay. Now listen here. First the description of the figure. First the diagram is this way. There is the source S. Here there is the lens. Source of the monochromatic light is placed on the principal focus. Therefore, the reflected ray by the convex lens becomes the parallel, and behaves as a plane wave. Now there is the slit LN. There is the midpoint M. So these waves are incident on slit. So according to the Huygens principle, all the waves are reflected by there is the screen. So all the point of the slit behave as an independent secondary source and produce the secondary wave. So here in one direction the waves are propagated. Here we consider 2 point C. 2 point C. That is the C point on a screen. Some are also propagating this direction. 2 point P. 2 point P. This point P. These plane waves are focused by the another convex lens on the screen is placed at the principal focus of the other lens. Due to the superpositioning of this wave, the interference pattern is obtained, and as a result, the constructive and destructive interference are formed. Thus, some points are shown bright and some are dark. There is the source. Convex lens. So, as shown in figure. A source of monochromatic light is placed at principal focus of a convex lens. So the light emerging out from the lens is parallel. So plane wave fronts incident on a slit. So there is the plane wave front. Incident on a slit. According to the Huygens principle, all points of a slit behave as an independent secondary source and produce secondary spherical wave. These waves are superposed on each other and produce the interference. Which is focused on the screen, is placed at the principal focus of the others, which is focused on a screen, placed at focus of a other convex lens. Due to constructive and destructive and destructive interference The bright and dark fringes are obtained. The bright and dark fringes are obtained on the screen. So that is the arrangement of diffraction by a single slit. Here is, so here only we discuss about the problem of diffraction. That is only for your understanding what's in personal diffraction. Okay. On the basis of this single slit diffraction, we have to now obtain the condition for central maxima, first order minima and first order maxima.